Okay, so today we're going to go over some math of thermo. So the goal here of what we're trying to accomplish is we started off with basically, the first law and the second law of thermodynamics. So that's U and S. So ultimately, we can derive all of thermo based on the relationship of U, V, and S. The problem is we don't have a machine that can measure basically any of these, right? We can infer the volume by, weighing it and knowing the density of things, but all of these variables are difficult to measure. So the goal of basically all of thermodynamics is to take these quantities and convert them into things that we can measure, temperature and pressure, namely. So we need to know some math. Basically, we need to know two things to accomplish this task. We're going to use multivariable calculus and the Gibbs phase rule are the two things that we're going to use to assess this. Because if we look at degrees of freedom analysis, we have three sort of unknown variables. So we need to define two. Which means that if we expand any one of these three variables, we have to expand it with respect to two others. So the one thing we have to keep in mind in thermodynamics is that everything is a function of everything else. I cannot independently change any variable without affecting at least something else in the process. Right? Everything is connected. I cannot just change the pressure without changing the enthalpy or whatnot. So everything is a function of everything. So if you see a T or you see an S or anything like that, unless you explicitly know that you're following an isentropic path or an isothermal path, that function is changing. And so that comes down to why we have to do the calculus the way that we do it. Okay, but the ultimate goal is these variables are terrible, these variables are nice. But unfortunately, the universe is constructed with these variables in mind. So that's all we're doing for the next basically, couple days is just converting from variables we can't measure to variables we can measure, and we have to go through a little bit of tedious math to get to that point. But what we're going to do here, zero assumptions at all. The only assumption that we are making right now is that calculus is valid, which I have some good faith in that, and that we only have to define two of the three variables of the universe to talk about things. This is for a closed system, right? But if you do an open system, you also have to include mass or number of moles, whatever the case is there. Okay. So where we left off on Monday is we had the combined first and second laws of thermodynamics. du is equal to T ds minus P dV plus, we could do either G dN or plus G dm. Ultimately, it doesn't matter, right? The units should give us units of energy. In this case, the G is going to be joules per kilogram or joules per mole here. So ultimately, these units should give us units of energy for dimensional homogeneity. And we can see already that we have U, S, and V. Right? So we've related a change in energy to a change in entropy and a change in volume. But we don't have an equation that tells us volume is a function of S and U and so on and so forth. So we have to manipulate this to get us something in somewhat more of a useful form. Quickly before we do that, we're going to take the same combined first and second law, and we're going to reorganize it for some other common thermo variables. Again, no assumptions are being done here. All these equations are the combined first and second law, just rewritten in a slightly different form. So if we rearrange this expression, we can write ds is equal to du over t plus p over t dv minus g over t dn. If you satisfy this equation, you're never breaking any thermodynamic laws. We can define dH as du plus dPV. So who remembers from their calculus how we handle this? What is the rule that we use?
dv plus
Product rule. That's the name I was looking for. Because everything is a function of everything else. So we have to treat every variable as if it's changing. Right? So we can't just assume pressure or volume is constant, because we're doing no assumptions at this stage of our work. So we have du plus p dv plus v dp. Now we will substitute du right here, and then we can take it and rearrange everything. This is equal to t ds minus p dv, and I'm going to drop the underbar because this will be for an open system, plus gdn plus p dv plus v dp. So we got two, oh, I lied. Drop the underbar. So two things cancel out here, this and this. So dH is equal to TDS, and what do we have here? Plus VDP plus GDN. Yes?
What does the underbar mean again?
Okay, the underbar, so V underbar, in this case here, means meters cubed per mole. And V is just meters cubed. So if it's an open system, we can have material entering, so we're concerned more with the total volume of the system. If it's a closed system, then we just care about basically the density of the system. Because, yeah, V underbar is equal to 1 over basically the density. And the nomenclature in the Sandler book that I will try to keep to the best I can is that the hat is specific with respect to mass, and the underbar is with respect to moles. But one of the criticisms of the Sandler book is it's very tedious in terms of its nomenclature. But it's useful, so it's a really good reference book, but it's a little bit cumbersome if you've never seen the material before. So in a class like this, I think it's perfect. Okay. So let's do the same thing for A, but I'll hand it off to you guys to finish out the work. So A is defined as U minus TS. So solve for me what dA is equal to as a result of the combined first and second law, using the product rule in all of its glory. And I'll rewrite this just so you guys have it, that du. Who's got it? A few folks. Okay, so I'll just put it up here. So dA is equal to minus S dt plus, minus minus P dV plus G dN. Okay, so yeah, so I put the du up there because you'll need to, so the procedure, right, is that we would just do du minus TdS minus S dt. Okay, so, and I'll just put up really quickly what dg is equal to as well, to facilitate discussion. dg is equal to V dP minus S dt plus G dN. So a couple of things we've noticed. G shows up an awful lot because it's very useful, right? So this is oftentimes called the chemical potential. So it's a very robust sort of a variable. But a couple other things. You'll notice that as we change from U to H to S to G, things are moving around a little bit to be a little bit more convenient. In the case of, we go back one slide, if we look at H, it's now a function of S and P. Well, that's helped us out a little bit, right? We can measure pressure more easily than volume. Excuse me, but we're still left with this really sort of annoying entropy term. If we look at A, well, now we've removed that annoying entropy term, we've still got this volume term. But with dg, pressure and temperature. That's why the Gibbs free energy is such a nice, convenient variable to have defined, because it's organized in a way that makes it easy for us to analyze. So oftentimes you'll hear that sort of the native or fundamental units of U are going to be S and V. For H is going to be S and P. For A is T and V, and so on, and G is P and T. Right? That's because it's the simplest way to sort of account for changes in those particular variables. So the other reason why is because you can very easily derive thermodynamic identities. And so we did this a little bit in class earlier. If we were to take, for example, the U expression, du is equal to T ds minus P dV. We'll make these for a closed system. So we can use the chain rule of differentiation, right, to expand out du with respect to any number of arbitrary variables that we want to. Right? In the case I used the example of your bank account. What's the rate of change of how much you make versus the rate of change of how much you're spending? Right? But in theory, you could have lots of different sources of income and lots of different sources of expenses. In the case of thermodynamics, right, we only have to choose two, because it's a closed system, and we have the Gibbs phase rule. So in this case, we only have to expand du with respect to two variables. So the total change in U, right, this big D, is equal to the specific change of du, and in this case, we're going to be smart about it, and we're going to choose S at constant V ds plus du, these need to be underbars, okay, so essentially what we're trying to do is we're trying to look for the total change in the internal energy of the system. And instead of just doing it going from point A to point B, we're going to break it into two steps. We're first going to walk along a path of constant volume, right? So here, we're walking along a path of constant volume but changing the entropy. Then we're going to walk along a path of constant entropy while changing the volume. And that accounts for the total change from state 1 to state 2. But you can see, right, this is how we define the identities. This expression is directly equal to this. This expression is directly equal to this. So when you expand your thermodynamic variables with respect to their native units, you can very trivially derive thermodynamic identities. So we had already derived these ones already. Du ds at constant v is equal to t, or vice versa, you could do the reciprocal of that, right? ds du at constant v is equal to 1 over t. And we can do this right here, like just take the reciprocal of the thermo function, because in general they're all going to be well defined. They're not going to have any discontinuities, and so we can just very trivially take the reciprocal. And in fact, most all of these should never equal 0 as well either. And then lastly, du dv at constant s is equal to minus p. So we could do this for all of the other variables, for h, for a, for g, and we can derive a total of 8 identities. So if you are to look on the sheet that I passed out, they should already have been derived for you. There's a total of 8 thermodynamic identities. And these are super useful because these are what we're going to need to rearrange, right, basically this annoying expression here to say, how do we calculate the internal energy as a function of temperature and pressure? That's what we care about. So we're going to need these expressions to rearrange this du equation that we can actually get a useful and convenient way to calculate u, to calculate h, and so on and so forth. Okay. So the next step then is, let me just go over 2 additional rules sort of that we'll need for the calculus here, for the derivations, and then we'll go into some more examples. So we have the chain rule. And I'm just going to use arbitrary variables x, y, and z just to define the chain rule. And we have dx, dy at constant z. Now the way that I remember to do this is that you just sort of rotate the variables in a circle. dz, dx at constant y, dy, dz at constant x is equal to negative 1. So this is a way that you can sort of restructure a partial derivative that is in units that you don't like into getting into units that you do like. And so the way that I like to remember how to do this is that you kind of just rotate your variables like this and do that, a couple times. We have the chain rule. And these can all be described by just taking out the, just doing an expansion. So these can all be derived readily, but we won't go over that. dx, dk is just some other arbitrary term at constant z is equal to dx, dy at constant z times by dy, dk at constant z. Right, so you can sort of see how the math just lets it cancel out. So you could see this dy just being canceled out, and you get the same thing again. So when we write out these expressions here, like du is equal to tds minus p dv, we can really use this with respect to any other variable, right? So we could say, well, with respect to time, or with respect to volume. So in theory, we could just say, okay, let's say du dt. Right, so we can just choose any other sort of independent variable that we want to change. And this relationship has to hold true. No matter what I do, whether it's time going on, changing the temperature, changing the pressure, changing the volume, no matter what I choose, this combined first and second law has to be true. So that big D total differential on the top, I can choose to vary that with respect to any other variable in the universe that I choose to. Temperature, time, pressure, volume, whatever. So these are going to be our starting points to get to the derivations to turn things into useful functions. So one other thing that we need is Maxwell relations. And Maxwell relations depend on another property, that the order of differentiation doesn't matter. So if we were to take, let's see, let me go find examples here. If we are to look at d dz at constant y of the function dx dy at constant z, this is exactly equal to if we said d dy at constant z So if you've got a two-variable function, it doesn't matter if you take it with respect to variable 1 or variable 2 first. The end result should be the same. So in this case, we could also say that dx squared, or no, so d squared x, got to get my math right here, is dz dy. This is equal to d squared x dy dz. That's essentially what we're saying. Right? So it doesn't matter the order that you take the derivatives when you do this. Okay, so to derive the Maxwell relations, our starting point is we take two identities and take advantage of this rule up here. So we're going to show how this works out. It's a little bit confusing, so I like to break it down into a large number of steps. Okay, so the two identities that we're going to start off with are du ds at constant v is equal to t, and du dv at constant s is equal to minus p. Okay, so we're going to then swap basically this ds and dv. So we're going to kind of take the derivative of the other one. You'll see in a second what that kind of amounts to. So what we'll do then is we'll take d dv at constant s of this function here, du ds at constant v. And then conversely, right, we can do the same thing here, d ds at constant v of du dv at constant s. Then we're going to use the thermodynamic identity and substitute that in, so that this is equal to d dv at constant s times by t, right, because we just substituted that thermo identity directly in there. So this is equal to dt dv at constant s. Likewise here, we're just going to substitute in the thermodynamic identity. So this is d ds at constant v times minus p. So this is equal to minus dp ds at constant volume. So these two equations are equal, right? It doesn't matter the order that you take the derivative, so we can just swap out that denominator and change the order. And so from here, we've derived a Maxwell relation. dt dv at constant s is equal to minus dp ds at constant v. And if I didn't screw up, that should be on the sheet that I handed out. Where is that one? Yes, there it is. Oh, there it is, yep. The top left one. So in the homework, you'll have to derive thermo identities and Maxwell relations, but for open systems. In the book, it does everything for the closed systems. So you'll have to do the additional step that instead of doing it for just two variables, you have to do it for three, because you also have that dn term in there. So that's one of the homework problems. Okay, Any questions on the math? So we're going to use it now to rework basically some of the variables. Okay, so what we're going to do now is we know that u is best written as a function of s and v. But let's just say, for example, let's just try and expand it with respect to some other variables and see what we get out of it. So let's just say, let's just try and just expand u around t and v. So we just want to know how is the internal energy changing with respect to changes in T and V. And let's see what we get out of this. So that gives us, so du is equal to du dt at constant V dt plus du dV at constant T dV. So does anyone recognize this first term here?
Yeah, we have Maxwell relation for it.
Well, so this is a very common definition, though.
Isn't that the heat capacity?
This is exactly heat capacity. This is C sub V is defined as du dt at constant V. So what we have done in thermodynamics is we have not solved the problem of how we actually know how to calculate u with changes in T. Instead, our solution is let's just calculate it, or let's just measure it. So whenever you see C sub P or C sub V, this is a variable that we could not figure out how to calculate or how to manipulate away. So the only way that we can satisfy this particular problem here is to just say, okay, whatever, let's just measure it. So that's why I really like to stress that we're teaching the system here. So all the C sub P's that you see, in this case here, C sub P is defined as dH dt at constant P. So it's a very similar derivation. So we just said, you know what, let's just measure it. Right? We don't know how to calculate it for different materials. We don't know how to predict it yet. With statistical mechanics, we can come closer to predicting it. Right? Especially for like an ideal monatomic gas or an ideal diatomic gas or even polyatomic gases. But when it comes to very complex mixtures like liquids, then we kind of still have to rely on just measuring this term. Okay, now the second part, du dV at constant T, we can write this as T ds dV at constant T minus P dV dV at constant T. So this top half here, T ds minus P dV. That looks familiar, right? That's just the combined first and second law. So we just substituted, right, that into this expression and then just took the derivative with respect to the volume here. So this far term here, dV over dV, that just goes to 1. Simple enough. And again, this is sort of like after the fact. Like when you're working through these derivations, you don't know which product rule or chain rule or triple product rule is necessary. Right? So this is sort of showing the pathway that can be done. This variable here, ds dV at constant T, that's not very pleasant to work with. But fortunately, we have a Maxwell relation. So this is equal to dP dt at constant V by a Maxwell relationship. So what we ultimately have here is that the end result of expanding du with respect to V and T is that du is equal to C sub V dt plus T dP dt at constant V minus P dV So this is not particularly clean, but this actually turns out to be an extremely useful expression. Because if we rely on the fact that we will just measure C sub V, right, then we know how the internal energy changes with respect to a change in temperature. Now this expression right here, there's something very unique about the variables in this expression. We only have P, T, and V. Rather, I'll include up in here. What do we call a function that relates between P, T, and V for a fluid? I think I hear a couple murmurs. That is one of them. What's the general term for equation of state? This is an equation of state. EOS, or equation of state. So in this case, the ideal gas law, PV equals RT. Or oftentimes you'll see it in in some texts as P is equal to, let's see, rho RT as well. Especially in like statistical mechanics texts, it'll write it like that. So the cool thing about equations of state is it's not just to sort of estimate what is the real density of the gas inside of this tank at this pressure and this temperature. Right? That's sort of the lowest form of application of an equation of state. Right? So when you're asked, like, well, what's the actual density of gas using the ideal gas law versus the van der Waals equation versus the Peng-Robinson equation? That is the lowest form of usefulness of an equation of state. What we really care about for an equation of state is this expression up here. We want to know how can we calculate everything that we need to know with thermodynamics from an equation of state. So all we need to know to calculate the properties of any real fluid are essentially some limited experimental tabulated data and an equation of state. So we can do all phase behavior, all thermo properties, all energy balances. We can do almost everything we can with just an equation of state and some heat capacity data. So that's why we really care about equations of state. It's not just this silly tank problem that we would deal with. It's really, this is the issue here. So what we've accomplished, though, in this sort of example, is that we've come up with a function for U as a function of T and V. No entropy. That's fantastic. Right? We've gotten rid of entropy. We can, in theory, apply this. Right? We can walk a path of constant temperature, and we can walk a path of constant volume, or in this case, constant density, and we can figure out the properties of materials. So we can do an energy balance now with some real fluid, not an ideal fluid. Okay, any questions? So we're going to do the same thing now with entropy.
I remember back actually real quick. I mean, just starting with the main equations, like you know how you had us do the early differentiation, there where you had like U minus equals blah 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 without any derivatives. I remember deriving the Maxwell relations by doing the derivatives there, then partial derivative, and then you got the Maxwell relations. I
think it's the same pathway then.
Oh, okay.
Yeah, because what we started with, going back to that question, is where are we at? Okay, so that first step is you start off with the combined first and second law, which is, go way back. Yeah, so we start off here, right, with this du TdS minus PdV. Right, so then that's basically, we take partial derivative here, right? And then we use that to relate the T and the du and ds and the P and the du and dV. And that takes us all the way up to here, where we then take the partial derivative again and take the partial derivative again. So it's the same procedure, I just sort of broke it down into slightly different steps. So I think it's the same thing. But basically, yeah, you take two partial derivatives, do a little switcheroo in the order, and you come up with the Maxwell relations. Okay. So now, let's do entropy. So with entropy, let's expand entropy with respect to, we will do T and V in this example. T and V. So this will give us a function that we can use to calculate the entropy of a real material with respect to changes in just temperature and volume. And likewise, we could do a similar thing for temperature and pressure as well. So ds is equal to ds dt at constant v plus ds dv at constant t. All right, so what we've done here as a reminder is we've just done what we call a total derivative sort of expansion using the chain rule. But we know that we only have to do it with respect to two variables, t and v, because of the Gibbs phase rule, saying that we only have to define two variables for any single phase system. So really, all of thermo is built on that assumption, right? You have the first law, the second law, and basically that there's only three variables that define the universe. So from there, it hopefully makes a lot more sense why, because I think the first time that I saw this, at least, I thought it was all arbitrary. I was like, well, why you only do two? Right? So the main thing is to remember that there's only three variables that define everything in thermodynamics. Okay, so we're going to break this into two portions. We're first going to manipulate this expression, and then we're going to manipulate this expression. Because, I mean, I don't have an equation off the top of my head that relates S and T, right? Because if we had that, right, so if we had an equation that directly related S and T, well, we would just take the partial derivative of it and plug it into this expression here. But since we don't, we have to get it into a form that's easier to measure. More often than not, it's an equation of state. So ultimately, we want to manipulate these expressions to get them to look like an equation of state if we can, because then we can use it as predictive. Okay, so on step one, we know this after the fact, but if you were banging your head against the wall trying to derive this, we would have to try a bunch of different things. We're just going to do the chain rule. So ds dt at constant v is equal to ds du at constant v times by du dt at constant v. So now we're going to use a thermodynamic identity, and we're going to use a definition. What is ds du at constant v equal to? This is something we've seen a couple of times. Is a thermodynamic identity. 1 over t. Du dt at constant v is equal to c sub v. That's a definition that we decided that would be useful. Again, who decided it would be useful? Someone back in the day. So this is equal to c sub v over t. That's something we can handle. If someone has tabulated c sub v values, all we have to do is integrate this function with respect to t. And that's where you get this, because when you integrate 1 over t, you get a natural log. So that's why those natural logs always pop up in the entropy equations, right? Because this is based on the definitions. So we've done no assumptions so far. This is good for solids, gases, liquids, everything. No assumptions. Everything we've done to this point in the class is assumption-free. Okay, now step 2, we are going to relate this expression here, ds dv at constant t. Well, this is actually quite convenient because this is actually a Maxwell relationship. dp dt at constant v. Is this the one that we defined actually? Not quite. Okay. So, we've accomplished our goal. How do we know that this is a good endpoint? Because we've basically come up with an expression that we can solve with an equation of state. So now if we rewrite this, we can write ds is equal to c sub v over t dt plus dp dt at constant v dv. Question?
So in step 1, how did you know, we'll use du?
How do we know to use D? Oh, the first in this this one here, you mean? Okay. Because we're teaching the system. That's basically the main reason. So in theory, there may be different ways to reconstruct all of thermodynamics. But ultimately, what it had been boiled down to, I guess probably after years or decades of trial and error, is how do we come up with the easiest way with the limited number of measurements to tabulate all of the properties of materials. And as it turned out, measuring heat capacity was probably the easiest thing to do. Because back in the day, they didn't really know how the energy was stored. So the quickest and the most efficient way to get to that information is say, okay, well, I'm just going to put a joule's worth of energy into the system and see how much its temperature goes up. And then from that, we can tabulate different information.
So it started with trial and error.
Yes, exactly. All of this was trial and error. And so again, so this was all, this thermo theory was developed over the course of maybe 100, 200 years, with people getting a little bit better and a little bit better. But I really like to stress we're teaching a system here. I don't have the answers for you. And classical thermo can never give you the answers. All it will allow you to do is tabulate data and use that data to calculate new and interesting problems. Because the cool thing about it is if I know what the heat capacity of water is as an ideal gas and an equation of state, I can calculate everything. I can do an entire Rankine cycle for power generation. I can do a steam engine from just basically two pieces of information. An equation of state that fits the properties well, and the heat capacity of an ideal gas. That's it. And so this is sort of what they thought was, this seems like the easiest way to do it. Let's just keep doing it this way. The classical thermal can never give you all the answers. Stat mech can give you all the answers, but the problem is molecules are so complex that we have to do a lot of approximations. So it's really a battle of, should we just measure it, or should we try and predict it from first principles? So let's just do a really quick example here. Let's go back a little bit here. Let's just, for the sake of fun, let's just apply this equation for an ideal gas, right? So let me rewrite this on a new page, just so we don't get lost in the woods. That's just what I want to accomplish here. Okay, so du is equal to c sub v dt plus t times dp dt at constant v minus p dv. Let's just calculate this for an ideal gas. Just to see what would happen here. So ultimately, what we're trying to accomplish here is if we had a plot, right, of u as a function, sorry, we want, my bad. We'll say v as a function of t. We have some state 1 and some state 2, right? Let's say this is u1 and u2. Our goal, right, is to go along a path of constant t and then go along a path of constant v until we can go from state 1 to state 2. So we're just going to integrate this expression twice. When we go along a path of constant t, right, this first term goes away. When we go along a path of constant, so this term will go away, constant v, this term will go away. So let's just really quickly calculate this expression here for an ideal gas. Because we already know that the c sub v expression is just something we're going to tabulate. Okay, so the ideal gas is PV equals RT. So I'm not very good at calculus. So what I like to always do is just rearrange it like I remember, like y equals x format. So I'll just rearrange this to be P is equal to RT over V. So then dP dt is what I'm looking to do, at constant V is equal to R over V, right? So now we'll just plug it in directly, right? So we have T times dP dt, which as we found out was just R over V, minus P. Well, as it turns out, P is actually equal to RT over V. Well, isn't this convenient? That's 0. So what we learned is that the change in internal energy of an ideal gas is independent from its density. Likewise, we could do the same analysis and show that it's independent of pressure as well. So when we calculate delta U for an ideal gas, so delta U for an ideal gas is just equal to the integral of C sub V dt. And that should be an expression that looks quite familiar to most everyone. But for a real fluid, right, the change in volume definitely changes its internal energy. But for an ideal gas, it doesn't. Right, ideal gases, they don't feel the effect of density. They don't know that other molecules are nearby. So this is the utility of what we're doing in this process here. Okay. So we're short on time, so what we're going to do is we're just going to rattle off the two other additional ones. So right now we've done S with respect to V and T. We've done U with respect to T and V. So now let's just do really quickly S. So ds is equal to C sub P dt plus V minus T dV dt at constant P dP. Again, this is basically, we're doing exactly the same thing we did in the initial example, except we're just expanding it. Instead of respect to T and V, we're expanding with respect to T and P. And then we just have to use different Maxwell relations or different thermodynamic identities or different little tricks to get into the right form. dH is equal to T ds plus V dP. So for this one, we're kind of just going to cheat a little bit. And we're just going to substitute the ds into there, do a little rearranging. dH is equal to C sub P dt plus V minus T dV dt at constant P dP. Okay. So what we have accomplished now is we have taken our entirely abstract starting points. I mean, the first law makes a decent amount of sense. It's just energy conservation. The second law, it's just kind of a rule that we're going to follow. So by noting that we have U, S, and V as the primary variables of the universe through just basic calculus, or multivariable calculus, I guess it's beyond a little bit basic, with multivariable calculus and the Gibbs phase rule, we have now restructured our entire foundation of thermo to be functions of T, P, and V, which we can actually measure in the real world. Yes, question?
What happened to VDT?
Yeah, the TT.
VDT, I think it cancels out maybe. Let's see. I'll have to, I'm kind of jumping ahead and not going over the stuff here. VDP. Oh, that is this. This V is right here. That is this guy here. Did I make a mistake somewhere? Let me double check here what's going on. Oh, no, guys, I'm sorry, I screwed up. This entropy equation is wrong. I jumped ahead. The entropy equation is, I can go back and fix this. Yeah, these conveniently terms are gone. Sorry. Yeah, nope, that's wrong too. That's what it is. What I did actually is I think I actually copied down the the final result for the enthalpy for the entropy. This is what happens when you skip steps, guys. Okay, this is right. Yeah, ds is equal to C sub P over T dt. That looks familiar to the U one. And then V over T, yep, dP. Okay, yes. Yes, we are good. Thank you for pointing that out. But these expressions are also on the handout. this table 6.2-1, some useful definitions in thermodynamic identities. It's sort of an underselling. This is basically all of classical thermodynamics on one page. So now all we need, and all we're going to do for the next little while in the class, is grab an equation of state off the shelf, grab some tabulated data, and calculate state changes in materials. Because we've restructured everything into variables that we can actually measure, P, T, and V. And that's why equations of state are so neat. Now, with respect to A and G, so we're just going to find, right, G is defined as H minus TS, and A as U minus TS. So basically, with what we've already done, we can just substitute those in, and we can come up with expressions for dA and dG with respect to PT and V. So the math is really important, but arguably, thermo's a really developed discipline, so you don't have to do too much math, right, because it's already really been done, because all the practical problems have sort of been solved already. But it's really important to know, I think, where we came from. So you will have to do a few derivations here and there using like the triple product rule and things like that. But for the most part, you know, a lot of people just sort of slips their mind after class is over because for practical problems, it's sort of already been worked out. Okay, cool. Any questions? All right, see you guys on Friday. Oh, and look at the homework.